Okay, so this is the paper I was recommended to read in terms of just to close up on the Primachief Rule, and I've been quickly scanning these now, and I'm quite like so. There's some things that I want to take a look at. First of all, the paper talks about um, the Primachief Rule is a promising approach to evaluating gradients of parameterized quantum circuits. Blah blah blah. The Primachief Rule states that if the generator of the gate G has only two unique eigenvalues, E0 and E1, then the derivative of the circuit expectation with respect to the gate parameter is proportional to the difference in expectation of two circuits with shifted parameters. So this is, and at least here is put in a more, kind of neat way. So you've got like the general formula in here. What is the generator of a gate? Because whenever I hear the word generator, I feel like group theory or something. Gate generator. Or quantum gate. Generators and roots of quantum logic gates. What is this? So this is the position of the quantum logic gates to establish general relations fundamental quantum gates. The explicit form of the generator and roots of matrix gate. So finding the generator of a logic gate helps understand the underlying logical operation, while any root of a given gate is itself a new gate. I guess what they just mean is the matrix, but I'm not so sure. Now, so the two unique eigenvalues is what kind of, what makes, so it's not the symmetry that I was talking about, but it's this, curious to know why is it like that it's two eigenvalues, and maybe that's kind of what really gives, because if I remember well, let me just open up the, portfolio stuff. Should be the notebook, because if I remember well, yeah, when I was just playing with the y and x and power rotations, they all kind of had like, and they do have two unique eigenvalues, 1 and -1, right? And actually they do then like actually have the so you have the eigenvalues, right? They do have like, I mean, if I just calculate the eigenvalues of z, so did I import all these? I think so. Z of x and of z, like you do have like these. Now the question is if the paper means like strictly two unique, or like if it has more than two but uniquely looking at it it's just two, then it's an odd, because that really kind of let's see, Twitter, where was I? That really, when you do these, when your circuit is just like these, right? And you even just have like a 1 qubit. Oh. And then you do the 2D plotting. That's what you get, right? Like it's that symmetry which really allows you to do that. As soon as you add like Okay, but it's about the gate, really. So the problem that I'm having here is this is really about the gate. Like if I'm adding another qubit, and this qubit just has like say like x packet exponent like whatever, right? Like so, but we're just parameterizing one. Sorry, these should be, we're doing, so we're doing the ZZ, and I should change this because it, yeah, whatever. Oh God. Like, I just don't see the symmetry here. That's the thing. The thing is that that just becomes quickly messy, right? So that's what's not clear. Wait a second, we're not talking about, we're really talking about, yeah, that's wrong. So we're really talking about the condition is not on the observable eigenvalues, it's on the gate's eigenvalues. And so if the gate that I'm using is the Y gate, but really like what we're having here is actually like the Kronecker product of these two, that will be the gate that we're having. So but I think that's what the paper is claiming, is that you can if you can decompose that, then it's fine. But because if I'm now, okay, so let's do it like these. So what's the gate of the x, the y pow gate? What's the matrix? Can I get I mean, I guess it's so circ. Okay, unitary matrix. Gate. I just want to make sure I don't make mistakes. Okay. Circuit. Oh, get the circuit's unitary gate. That's what I want to do. So once I have the circuit, I get the unitary, if possible. Okay, cool. I like that. So it's not the observable. It's really, yeah. Right? If the generator of the gate G, and that's the unitary. Yeah. That's not like A here is the observable. Okay, cool. So if I have the circuit, and I now say print me the circuit unitary, please. Please. Okay, do I have to actually give it like, I think I have to give it a, yeah, there you go. Okay, so you have these. Cool. If I do, uh, if I do print the eigenvalues of that, so what I want is the unitary, and then what I want is the circuit eigenvalues. And so we want these to be here. I don't think that's what I want though. Yeah, so you've, as you can see here, okay. So can I just add this modifier here? Doesn't matter. Because I see it's a, oh yeah, no, as int, no, it should be just the complex numbers, shouldn't it? Wait a second. Yeah, correct. Okay, the fact is that they are, the fact is they're not like unique, right? So they're not two of them. So it's 1 plus 1 plus 1j, like, or almost, because it's really small, e, like minus 16. 2 plus 1 minus 1 plus, yeah, almost kind of 0 effectively. 0 plus 1. So basically, they're not too unique, and so this means, in theory, you should not be able to apply these into this circuit. Now, that is why this differentiation rule shouldn't be applied here. Now, this claims here that if you can break these down into gates where you can do that, that should it should work. Gradients of such concept. Okay, so yeah. Promising approach to the classical optimization step include gradient descent. The Primachief Rule approach to quantum gradients can only be directly applied to gates with two unique eigenvalues. However, herein we will discuss how parameter shift gates can be evaluated for a much wider range of parameterized gates using the product rule of calculus, provided we can decompose our gate of interest into a product of gates, which each of which is parameter shift rule differentiable. We will exactly, but that's the key, right? It's parameter differentiable. Each of which is parameter shift rule for 2-qubit gates discuss simple gate decomposition in detail. Okay, let's try to do this. So in classical simulations, we do not need to resort to the parameter shift rule, since we can apply non-neutral operators to. We'll conclude with a discussion of how to efficiently calculate gradients of quantum circuits on classical hardware. Let us review why the parameter shift works. Suppose that the generator of the G2 gate is unitary as well, and then the prefactor, then G is also idempotent. And with Euler's identity, we can express the gate as, okay, so that's the idea why this works, is because you can express because you can express the gate like this, and because it's a cosinus and a sinus, in those both cases we know that this differentiation rule works. This is why. not sure I fully understand it, but like if I see these, I get it. So just thanks to the fact you can express it like these, then you can do the differentiation. The key insight is that even if G is not unitary, if it has only two unique eigenvalues, then we can always convert the generator AJ to a unitary operator by adding and multiplying by real constants. The additive shift can be neglected since it only adds an irrelevant phase. Therefore, for any real constant A and Hermitian operator G with two unique eigenvalues, we have these up to a phase. In the special case of 5, we have okay. Note that the derivative of the gate is okay. So yeah, the derivative of the gate is like you take the exponent down. No, minus IA G whatever. So we can now derive the Primachief Rule. So they go ahead and then okay. They replace these stuff. Yeah, kind of. We write out the gradient using the product rule, blah, blah, blah. Note that the value of the shift constant depends upon the parameterization. For instance, the 1-qubit Pauli rotation gates are all parameter shift differentiable with R1 half. Here the Pauli matrices. On the other hand, it can be more convenient to represent the same gates as powers of the Pauli operators. But in that case, the shift constant is pi divided by 2. Okay. How do you find that, though? How do you find the shift constant? I don't know. Primary shift gradient via gate decomposition. Okay. A direct application of the Primachief Rule requires that the generator of the gate have only two eigenvalues. However, we can evaluate gradients for gates that do not meet this requirement by decomposing the dynamics into a sequence of gates, each of which has a generator of the requisite form. As a trivial example, consider 2-qubit canonical gate. This gate is intrinsic to the 2-qubit gate. That's the reason I actually have these. I actually opened that because I forgot what those gates were. The Ising gates. But you can see already here that they also have this form. So in theory, if I could decompose like these, right, into yeah, well, I know I can because I know it's this y and this x. It's the canonical product of those. So I know I can because I just made it up like these. So, but how do I have to modify then the shifting? Has to more than two unique eigenvalues. Can with respect to any of the three parameters in the Primachief Rule. You can evaluate the gradient with respect to any of the three gate parameters because x, y, and z terms in the Hamiltonian all compute and the canonical gate can be decomposed into a sequence of x, y, and z gates. For these parameterizations of the x, y, and z gates, we have pi divided by 2. More generally, we can decompose any 2-qubit gate into a canonical gate plus 1 qubit gate. provided we can determine the functional relation between the original gate parameter theta and the parameters of the decomposition, we can evaluate gradients with the product rule. What is the product rule? Okay, that I can. Okay. Since an arbitrary Tokubi gate has 15 parameters, we may need up to 30 expectation evaluations to evaluate one gradient of a Tokubi gate. Note that there are many essentially equivalent choices as to how to parameterize the local 1-qubit rotations. We use the x, y, x Euler angle decomposition rather than the more common z, y, z. So what's these? The T1 figure 1, the T1 parameter and first derivative of the CR canonical gate. Decomposition for B 1/2 and 1 and 3/2, blue, orange, and green. Note that T1 exhibits discontinuities, but these are largely artifactual since same as, I don't know. And then figure 2, T7 parameter and first derivative of the CR canonical gate decomposition. The three natural parameters of the circuit can be expressed using elementary functions. CR gate. The procedure to decompose the CR gate is as follows. First case, the circuit answers by examining numerical decompositions of the CR gate. We're left with three undetermined parameters. Since the CR gate is equivalent to an XX gate, blah blah. Okay, so this is where it just goes to magic. Yeah, I think M is the magic gate, which transforms to a magic basis. What is the magic? I think I've seen this before. Magic basis. Magic states. Well, that's a nice magic PDF. Okay, whatever. Where was I? Here. Blah blah blah. In a classical simulation, okay, that's already not. I'm not interested in here. Okay, so that's it. I would still expect this to. I would still expect it to see visually. You know what I mean? I would still expect this to be seen like somewhat visually. T1 parameter. And first derivative 24, 25. So basically, as long as the circuit is made out of gates that have like two unique eigenvalues, then you should be able to apply the rule. But that means you should be able to apply it to kind of like everything, right? Because you can just compile down the circuit to all this stuff. I mean, I'm gonna see not to give interaction. Is parameters. The three non-trivial parameters of this circuit can be expressed using elementary functions of the CR gate. The procedure to decompose the CR gate is as follows. The first case the circuit enters maximum numerical decomposition of the CR gate. We're left with three undetermined parameters since CR gate is equivalent to an XX gate. Okay, so here what they're doing is they're trying to specify what those parameters look like with respect to the original theta. Is it that what they're trying to do? T1, T4, T7, T1, T4, T7. The CR gate is a natural gate for certain microwave control transmon superconducting qubit architectures. It's okay. It's these, and it's got S, B, and C. Canonically decomposes a circuit of one qubit gates and an XX gate. Okay, so there you go. The S. I was just looking for theta and I couldn't find it. S, B, and I'm missing C. Oh, here, C. Okay. So this is how you were. Then this is how you gotta parameterize these things. In this case. If you wanna, I mean, that's probably important, right? Like, because this means you're calculating the shift of these parameters. That's what you want. You want to shift these parameters, the S, the B, and the C. That's the ones you're trying to optimize. And so if you're using this decomposition, what you should do is you should calculate what's the shift of these, not like the T1s and T4s and T7s or whatever. And so that's the relationship. And those are the derivatives. So we can therefore calculate gradients of the CR gate by using the product rule. Add expectation evaluations using the Primachief Rule and the following derivatives. So you got to do the derivative of those parameters. I'm not sure I fully I'm not sure I would need to do this in a practical setup, I think, to better grasp. But I guess I know what is, because I'm just used to think about like I'm just used to think the things I'm just used to think in terms of like the typical gate, like from a, like you've got like the poly gates and you've got like the control not gate and all this kind of stuff, which like they all have already, they all fulfill the condition of the two unique eigenvalues. And so, you know, kind of talking about like a CR gate and these kind of things, maybe the U3 gate would be a practical example. Although I already know the U3 gate the composition is also a Pauli matrix. It's a Pauli So that doesn't also help. Whatever. I mean, I think it's just like kind of all good, but at the end of the day, regardless of all these, because that just tells you how you would need to calculate the derivative, right? Um, how you would really need to calculate the derivatives. Those are the shift parameters, I guess. You can calculate base out of these, right? Great. So Hamilton has 4 unique eigenvalues in general. However, if C is 0, there are only 2 unique eigenvalues, and the Primachief rule applies. Now that's smart. Okay, so here's they explain that if one of the parameters is 0, and you just add these, then this one has 2 eigenvalues, and then so you can just go ahead and do this. Okay. But still, okay, so still, so this is one thing. Then you need to find that shift. That's okay. I love to do that, but I'm like, I want to explore other things as well. But it's still, you should be able to see that visually, shouldn't you? Like regardless of these, like that's just a tooling. That's just something that tells you, okay, am I able to do these or not? But if I plot the thing as a function of the angle, okay, so if I'm just plotting, so if this is my circuit, I should at the end of the day see something that is like a repetitive pattern, right? I should just need to, like, the thing is, maybe the plotting that I'm using is just confusing. So that's the circuit, right? We'll call this alpha. Alpha. Cool. We're not gonna print these. And now let's not get too hanged up on the, let's not move, right? So let's just do like a static. I love it how Python is like, just don't indent me, man. How can I connect the dots and how can I make that bigger? So I want to do like a 50-50 and I want to have like fixed size. Like, why isn't this working? I want the figure to be bigger. This is working here, but it's not. It's just like these working, right? Am I not using this correctly? Well, I probably should put it before. I think I should just do it here. Yeah, there you go. Now we're talking. Now we're talking. Okay, and now I just want to make a scatter plot with a line. With a sequence line. Connected scatter plot. Yeah, that's all I want. Call maplet scatter plot with an X as a sequence of X around this. Call maplet plot with an X to connect each point in order. Okay. Okay. So if I just say plot. Oh, there you go. Okay. $50 plus $50. Like what do I see here? Too many points. But it's, yeah. Like, I get it. It should be. Like, it should be differentiable using these. Like, I don't know. It's a bit stretched, but I see it's a kind of like a it's kind of like a wavy pattern, right? Like if I sorry, that's the wrong one. There you go. I wanted to stretch it a bit more so I can see these better. That's yeah, I'm just stupid. Why didn't I do this before? Yeah, and now I can just say like give me like 100 and give me like way more precision, make that even bigger. Let's see what happens. Yeah, there you go. Okay, cool. Yeah. Now, what would be an example of something that's not differentiable? Just so I could see. Just so I could see the difference. But I think I'm gonna have to leave these for the next video. I'm really running out of time now. So there was a because the CR gate is not something that I can. Circ. Can I parameterize the swap gate? C swap gate, control swap gate, right gate. Yeah, okay. I'll see if I can do this. So I see if I can do this in the next video later. Later today. I'll just go back to these. I just wanted to kind of see a difference, get a, because for me, like I feel that's much more intuitive than just like going through the numerical part. Although the numerical part, like it's probably much more convenient. And at the end of the day, if you not convenient, but like formal, right? And if you really at the end of the day, you actually want to figure out how you want to differentiate this whole thing, then you better do the analysis actually and try to figure out what's the shift that you have to apply, what's the shift that you have to apply, and all that stuff, right? This is, of course, if you want to use the Primachief rule. Like, I guess you don't have to. I guess you can also just use other optimizer techniques, which we're going to take a look next in the next video, which is basically this paper here, low depth mechanisms for quantum optimization. I'm hoping that there's going to be some bunch of interesting stuff in here in terms of how to optimize circuits, just so I can, kind of be able to be more intuition around these. And I think I'm going to leave it here, like after this paper, and then kind of come back to the multiverse computing paper, the portfolio optimization one, and do kind of go back and actually finish up the Lagrange thing for the D wave, finish up like the tensor network stuff, yeah, and then basically just give it a quick run and see if we can just at least get something to run. We'll see. Would have been a long project, but I think it was worth, especially for these part. Like I'm happy that I dived into these. Like also the tensor network stuff. I think is going to connect a lot of the things, a lot of the dots that I want to, a lot of things that I want to explore later, later on. But now I feel a bit more confident about like knowing the details of these. Where it's like, okay, it's not just the Primachief rule shouldn't just work out of the box. And there's many more optimization techniques one can use, which we'll definitely explore. I mean, one for me is like one that it seemed obvious to me always is like, why can't you just like say take a look around your point and then just do a bit of a sampling around your whatever dimensional space you have, and then see where is it going down, and then just pick that direction, right? um, Sort of like if you imagine like a 3D surface, you just like take a look at a really small circle around you, and then in terms of your x and y coordinates, and then see see the one that's going down. Like it's a it's a naive one, but like why? Maybe it's naive, but like that seems to naive, not naive, but like inefficient. But that should work, shouldn't it? I mean, like it's like you know it's really like actually in the real world, just walking around and you kind of see where the hill goes down, right? And just follow that path, kind of. So you don't really need to rely on the derivatives. Probably the derivatives is just with the derivatives just makes it more efficient to calculate that. Because if you have like a higher dimensional space, it's going to be really complicated to take a look at your hyper or your high dimensional circle kind of around you, so to say. Um, 3, 4, 5 parameters. Yeah. Awesome.